Okay, so this is going to be the second part to the right-hand slap rule, and this is telling us how much force there is. And it's not very complicated, so I'm just going to tell you the formula, and then we'll dive right into the questions. Force equals nilb. N being the number of turns, I being the current, L being the length, and B being the magnetic field. And now we'll see if this makes sense. So imagine we have this current going through here, and we have this magnet, okay? If we had a stronger magnet, would the force get bigger? Yeah, that makes sense. If we had more wire for the magnet to act on, or more wire for the current to be carried in, would that make the force stronger? Yeah, because each piece of wire, like if you had a tiny piece of wire, imagine there'd be a tiny, tiny piece of force, a tiny force on that. But now we have that many pieces of wires, there'd be tiny forces everywhere. So basically, yeah, the longer the wire, the more force we have. I, the amount of current. If we have a big charge, remember that's what the field's acting on. If we have a big charge, that charge is going to start pushing much faster. And turns. So turns is like if you wrap coils around here. Basically, it's just adding extra, it's like adding another layer, okay? Because every turn means we have another layer of wire, okay? And that means we have a lot more force. So F equals nilb makes perfect sense. And in many cases, there aren't any turns, only if they mention it at the top that it matters. Well, here it says 50 turns. Anyway, now that we have that, because I like this diagram, we'll go back to an easier question, and one that we've seen before. So just to recap, here's all the numbers. This is current going across, and they say that the magnetic field is running from south to north. Right-hand slap rule tells us that we have a current going this way, our field going that way, means the direction is up. Just a bit of revision for you guys. Now we need to use F equals nilb. So we just look around for it. Hey, that looks like an I, and it's DC current, so we don't need to worry about root mean squared or anything like that. So I is 2000. How long is it? Well, the poles are 20 meters apart, so we have 20 meters to work on. So the units of this is amps, the units of this is meters, and finally we have a field of 4 times 10 to the negative 5 Teslas. So these are all the units, and this will give us something in newtons. Okay, why are we worried about N? Well, there are no turns here, it's just a single wire. So now we just need to calculate that. Let's figure this out. How do I exit this? I will give up in 2 seconds if I can't get this happening. Okay, I'm just going to do it in my head. Okay, so that's 2000. So we just multiply these together to give us 40,000 times 4 times 10 to the negative 5. So that equals 16, 1, 2, 3, 4, 5, because 4 times 4, I mean 4 zeros, times 10 to the negative 5. So to get 10 to the negative 5, we got 1, 2, 3, 4, 5. That's how many zeros we have to remove. 5 of them. So the magnitude is 1.6, because we've moved from 16 to 1.6. Okay? And that's kind of how you do standard figures, significant figures, because one of you asked that. Okay, we'll go on to this one. Draw an arrow to show the direction of the magnetic force on side JK. So we have JK, it's 5 centimeters long, but it doesn't ask for force, but I'm going to do it anyway, just because we can. So we have 50 turns up here. F equals nilb, I like writing it down. F equals 50 times I. What's I? I is a current of, it doesn't say, maybe that's why we don't need to figure out the force. But whatever, if we did have a current, we would put I here. We know the length is 5 centimeters, so we multiply by 5 times 10 to the negative 2. And finally our field is 0.3. And if we multiplied all that stuff, we would get our force. I'll do a few more questions in the next video.